Hey guys, welcome to section 7.1. In this section I'm going to show you how to apply the Pythagorean theorem. This might be a theorem that you've learned back in the day and maybe it's still with you and you still know how to use it. Others might have forgotten it, but either way we're going to do a slight review here and that's going to kind of set us up for section 7.2. So what the Pythagorean theorem says, or deals with at least, is definitely you got to have a right triangle. You can only work with right triangles, just like I have over here to the right. Okay. Now, like any triangle, it has three sides. Two of those sides are considered legs. They're labeled legs. And then one of the sides is labeled a hypotenuse. Okay. So what the Pythagorean theorem says is that the hypotenuse squared equals the leg squared plus the leg squared. Usually it's written out as the sum of the sides squared equals, or sorry, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the legs. That just gets sort of kind of confusing. So if you can just remember this idea of the leg squared plus the leg squared equals the hypotenuse squared, or in the case of how you kind of normally see it, you normally see it as a squared plus b squared equals c squared, with a and b being the legs and then c always being the hypotenuse. So c is always the hypotenuse. It really doesn't matter which leg is a and which one is b. For example, this one certainly could have been a and this one certainly could have been b. It doesn't really matter. Okay, so if we just kind of were to draw a basic example of this, you know, we can imagine something like this. I'll just draw a basic right triangle. Got to make sure it's a right triangle. Maybe one side is 8 and one side is 6. Okay, so we don't know. I can call this x right here. I could call it c. It doesn't really matter. So I know that 6 squared plus 8 squared is going to equal x squared. Okay, 6 squared is 36. 8 squared is 64. I don't know x squared, so I'm just going to carry that down. 64 plus 36 is 100, and that equals x squared. And then in order to get x by itself, you're just going to take the square root. And so the square root of 100 is 10. Okay, so that's just a basic way of how you get the hypotenuse. So let's just try a couple other few examples. Nothing new is going to be added to this theorem. That's just basically what it is right here in a nutshell is this, and it's basically whether or not you can use it. So we'll do a couple different examples where maybe I'll give you the hypotenuse in one of the legs and you'll have to figure out the other leg or some other different example. So let's just, by the end of this, let's make sure that we can use this theorem. So in this example, you can imagine a situation in which we have a ladder leaned up against a house. Maybe you need to get up to the house for some reason to paint or whatever, and the ladder needs to be a certain amount of feet away from the house itself, and you want to know how high that'll reach. Maybe there's something specific you need to reach, and so you want to know if it'll reach that high. So in this case, we know the length of the ladder itself, and we know the distance that the ladder is from the base of the house, but we do not know the height. Okay. We do know this is a right triangle because the house and the ground meet at a 90-degree angle right there. And so with that being said, because we have met all the requirements, we have three sides, we have a triangle, and it's a right triangle, we can use the Pythagorean theorem. So in the top right, it says a squared plus b squared equals c squared. My a and b are going to represent the legs, and then my c is going to represent the hypotenuse. So I'm just going to go ahead and fill this in real quick. So I can just do a squared. Oops, I didn't literally mean to write a. My a squared will be like 4 feet squared plus h squared, which is the height, and then equals 16 feet squared. And then I want to go ahead and solve that. So we have 4 squared is 16. I don't know h squared. And then 16 squared is 256. Okay, so from here you could subtract 16 from both sides. Then I'd end up getting h squared, bringing that down. 256 minus 16 is 240. And then finally, in order to get rid of, I want to get rid of this squared, and so I want to get h just by itself. And so in order to do that, I have to take the square root of h squared. And because I did it on the left side, I'll do it on the right side. And so h squared, the square root of h squared is h, and then the square root of 240 is about 15.5. So about 15.5 feet. Right about there. Alright, so that's how you go about solving for one of the legs of the triangle. We'll do one last triangle. I'll talk to you about Pythagorean triples, and then we'll be all done. So what if I wanted to figure out the area of a triangle using the Pythagorean theorem? Well, the problem in this example is that I don't really know the height. It's not given to me. I can sort of make a line to represent the height. I can just kind of come down here with the red ink and just split it right down the middle. And I can call that h if I want. The nice thing about that is it forms a 90-degree angle with the base at the bottom here. And the reason why I'm making the height, or at least I'm labeling it in the first place, is because we know that the area of a triangle equals 1/2 base times height. I already have the base right here, that's down at the bottom, but I didn't have the height, and so I'm trying to figure out the height of the triangle. And so what I've just done is I've split this entire isosceles triangle into two smaller right triangles, and they're equal in size, so both these triangles are congruent. So if I can figure out the area of, or simply the height of just one of them, then that's got to be the height of the other. And again, the whole purpose of this is just to figure out the height in general of the triangle, and then use that to figure out the area overall of the big triangle. So let's figure out the height. It doesn't really matter which triangle we do because they have the same dimensions, but since I split this whole triangle in half, that means this base got split in half, and so that means this is 5 and this is 5. Okay, so now, like I said, I have those two equal right triangles. So one of the legs is 5, so 5 squared plus h squared, because that's another leg, and then equals 13 squared. Another thing I should mention is that if you're ever wondering where the hypotenuse is, if it's not insanely obvious that a particular side is the hypotenuse, it's always going to be opposite of the 90-degree angle. Okay, so that's one way to always know for sure. So when we figure this out, 5 squared is 25, h squared I don't know, 13 squared is 169. And then from there it just becomes an algebra problem. So I can subtract 25 from both sides. These cancel out. I'm left with h squared equals 144. I'm going to bring this up because I ran out of room. So h squared equals 144. And so again, I want to get rid of that square. I don't want that square to be in there. I want it to be h just by itself. So I take the square root of both sides, and I'm left with h equals the square root of 144, which is 12. Okay, so the height of that triangle is 12, and that's good. We figured that out. That's the first step. But now I have to actually take this height that I just found out, and I have to plug it into this area equation from the beginning. So the area equals 1/2 the base, which the base of the entire triangle was 10, or is 10, so times 10, and then I just found out that the height is 12. Okay, so when I do that, 1/2 times 10 is 5, and then 5 times 12 is 60. So I could say area equals 60. And if this were in meters, it'd be 60 meters squared, or if it was in feet, it'd be 60 meters squared, and so on. But that's how you can use the Pythagorean theorem to solve for area of a triangle. So hopefully if you watched this video, be prepared to come to class the next day, and we'll apply some of these problems in a real-world setting to use the Pythagorean theorem.